You may not think about it, but this morning when you brewed your tea, you showed how transport is a part of our daily lives. Our team will be using tea to understand how diffusion works. Climate change studies have shown that increases in temperature and heavy precipitation decrease tea quality. A decrease in tea quality can be associated with a decrease in polyphenols. The amount of polyphenols in tea varies based on the temperature, type of tea, concentration of tea, and steep time. Modeling tea diffusion can help us understand how tea diffuses when brewed, so that optimal brewing conditions can be identified, and the model can be adapted to the changing climate conditions in the future. Our hypothesis is that as temperature of water increases, the diffusion coefficient of tea will increase. This project addressed many theories and concepts discussed in class that are related to mass and heat transfer. In microwaving the water, all types of heat transfer were observed, including radiation, forced and free convection, and conduction. We also looked at mass transfer in the form of diffusivity, which is the physical property of a substance that indicates the rate at which it diffuses. As the tea bag entered the water, the surface was disturbed, triggering a movement of the tea leaves in the diffusion of smaller tea particles. Molecular flux occurs due to the random motion of the tea particles based on the concentration gradient from the high concentration inside the tea bag to the low concentration of tea in the water. The diffusion coefficient is the proportionality between the flux and the concentration gradient. It is a physical constant dependent on the physical properties and temperature. These concepts were used to help develop a solution to our problem. To obtain the images of tea brewing at different temperatures, we microwaved the glass measuring cup for a specified period of time and measured the temperature of the water immediately after removing from the microwave. The water was then poured into a glass cup that was set in front of a white background. Once the tea bag entered the water, a picture was taken. Every 30 seconds for the next 5 minutes, a picture was taken for a total of 11 pictures for each temperature. On imageJ, a circle was drawn at 5 points on each picture to measure the integrated density. This was repeated for all 11 pictures for all 7 temperature trials. Finally, these points were pasted into our Excel sheet and the average was taken of all 5 points. This process was repeated for all 11 pictures for each of the 7 trials. After analyzing the photos for each trial, a graph of integrated density versus time was made. Then, Beer's law was used to convert to concentration. The concentration versus time graph showed that as time increased, the concentration of tea in the water increased for each temperature trial. Heat causes the tea molecules to move faster. At higher temperatures, the tea particles will take less time to diffuse from the tea to the water as more energy is readily released in a shorter period of time. The tea bag represents an area of high concentration of tea particles, while the water represents an area of low concentration. The greater the difference in concentration, the more rapid diffusion occurs. Plateau is reached over time as the difference in concentration between the tea bag and the water becomes smaller and steady state is achieved.
We chose 3 representative temperatures reaching an approximate steady state where concentration plateaued. We had to derive a new plot of transient concentration profile divided by the steady state function. The ln of this function reveals a slope that is a function of the diffusion coefficient. To proceed, we had to start with the shell balance, or fundamental species continuity equation. Since we're not stirring the tea with a spoon, there's no convective flux, and because there's no reaction, the equation further simplifies. The result is a partial differential equation with both a temporal and spatial solution. To solve, a generic solution can be found by separating the concentration into 2 separable ODEs. Boundary and initial conditions for each temperature were used to derive the following specific solution. After a lot of work, we can finally find the diffusion coefficient from the slope divided by the eigenvalue squared. Here's a plot of the diffusion coefficient at different temperatures. These diffusion coefficients were input into COMSOL to create the following animations.